computer. Hi, as you know, I'm still wearing the mask. I have to wear it till Friday, and then on Friday I can start moving about freely and not contaminate the world. So that being said, I talk a little louder with my mask on, so cover your ears if you have to. Okay, so the last thing we talked about was alkenes. Okay, and we saw that alkenes, we proved stability of alkenes with the heat of hydrogenation. And we saw that the heats of hydrogenation changed by the different structures of the alkenes. And that got us to this series where ethylene with only hydrogens on the double bond was the least stable of the set. And the one over here with 4 substitutions, and those could be carbons or oxygens. Any electron-rich material will do the same thing, okay? Now, these are more stable because of hyperconjugation, okay? Just the same way that the tertiary carbocations are more stable, okay? They were also more stable because of induction, okay? Carbocations, tertiary carbocations are more stable because 3 inductions from the 3 things attached to it and hyperconjugation, okay? The same 2 principles give these their stability, okay? So it's not magic. It makes sense because it works for several different things. Anytime you have an sp3 hybridized orbital and an unhybridized p, you should be looking for inductive benefits and the cancel display on. I just turned this display off on time. Anyway, so you're looking for those inductive effects and that hyperconjugation in the P. Okay, so that's going to give us our, a good way to look for consistent things throughout our system. In our sp3 hybridized carbons, we're looking for just inductive effects, right? In acids, we're looking for inductive effects, conjugation effects. But in the sp2 hybridized systems, we're looking for inductive and hyperconjugation. Okay, so any questions about that? That makes sense, right? That these are going to be more stable, and not only are they more stable, they're going to be less reactive. More stable, but then we also have steric effects, but they're more stable, so they're less reactive. All right, so let's talk about how to make these. We have 2 elimination reactions we are going to talk about with these, okay? The first one was the dehydrohalogenation reaction, okay? So we're going to remove an acid and a proton, and we're going to remove a halogen, okay? So we're basically moving HCl, HBr, HI, okay? So always look for the halogen and the beta hydrogen. The beta hydrogen is where the hydrogen comes off of, 1 carbon over. The other thing we can do is a dehydration of alcohols, okay? And in this case, we are using a hydrogen or proton, okay? So notice in the dehydrohalogenation, we're using a base. So the base is required for the system, okay? It's a base activated system, okay? In the case of the dehydration of alcohols, this is an acid activated system. In fact, this is an acid catalyzed system, and I'll explain why. Okay, so we have the remaining fact is we're going to remove 1 beta hydrogen, and we're going to remove something off of the alpha hydrogen, alpha carbon. It's either a halogen in the dehydrohalogenation or OH in the dehydration. Okay, so that is, and they have slightly different mechanisms, maybe. One's acid catalyzed and one's base mediated. They might have different mechanisms. So let's start looking at that. In the case of our dehydrohalogenation, we're going to be doing an E2 reaction most of the time. Okay, E2 reaction. What that means is that our base has to start tugging on our beta hydrogen at the same time. The electrons from our beta hydrogen are going to be moved in between the alpha and beta carbons. And the electrons that were bonded to the alpha carbon onto the halogen are going to leave with the halogen, giving us a Lewis base. Okay, so it is most of the time, it's going to do it with an E2 reaction. And in the E2 reaction, you're going to do that with a strong base or a strong hindered base. Okay, but it is possible to do it in an E1 reaction, but it doesn't work very well because you have to go through a carbocation. And it's in competition with SN1, and it can rearrange. So you would really like to try to make sure you're using the correct base to give us this compound. Okay, so to encourage the use of E2, we want to use a secondary or tertiary RX if possible. Okay, the reason we want to do that is we want to shield the carbon, the alpha carbon, so it doesn't substitute. So if we use a secondary or tertiary, it doesn't substitute. But we also can have the beta carbon. Notice it's not secondary or tertiary, it could be primary. So this is not hindered at all. Okay. If we have to use a primary alkyl halide, we have to use a bulky base. Write down bulky base equals potassium T butoxide. Okay. Let me write that down. All right. KO minus, and then 3 methyl groups on there. Right there. So this is potassium T butoxide, and it is our classical bulky base. Okay, so why are we using a bulky base here instead? We can use hydroxide here, but we're using this because the hydroxide would act as a good nucleophile and substitute. It would give us an SN2 product, or a mixed of E2 and SN2. So we're using that bulky base to fit. And we're also going to use a high concentration of a strong polarizable base. Okay. Now, the reason we want a strong base is we don't want it to form a carbocation, right? Only weak bases form carbocations. So we use a strong base. And then further moving to strong non-nucleophilic base like T butoxide will prevent SN2 reactions on the primary and the secondary. Remember, tertiaries don't SN2 anyway. Okay. So here's where encouraging the E2 reaction. Okay. Secondary and tertiary can use a strong base like hydroxide or alkoxide. Primaries have to use T butoxide, but the secondaries and tertiaries can also. Okay. So we also want to use high temperatures. Remember when we talked about the competing reactions, right? And so higher temperatures favor elimination. Lower temperatures favor substitution, right? Because substitution is kinetic and elimination is thermodynamic. So you want a higher temperature to encourage elimination. Okay, so we talked about regioselectivity in our and regioselective reaction, right? Regioselective reactions, and we talked about stereospecific reactions. Regio means we're going to specifically target one part of the molecule more than others. Okay. So the regioselective reaction is a reaction that leaves a predominantly or exclusively one isomer. So one isomer is favored, and you can kind of drive it in that way. So E2 reactions are regioselective. Okay, because you have your alpha carbon, so, and then you have to choose your beta carbon, and you're choosing your beta carbon that will give you the most substituted product. Wow. Aren't the more substituted alkenes more stable? So you're going to try to form the more stable product. So you're always going to try to form the most substituted product, if you can. So now let's look at this. We have this compound here. It is 1, 2, 3 carbons, and that, which makes it a tertiary alkyl halide. So that means we can use any base we want, as long as it's a strong base. Okay. Because it's tertiary, we don't have to worry about SN2 reactions. Okay. Now, we have a choice of a beta hydrogen on the methyl group and a beta hydrogen on the methyl group. These two beta hydrogens are equivalent. They're going to give the same product. Okay, those two sets of beta hydrogens, and there's a total of 6 of them. So you have 6 beta hydrogens in that set. But we also have these 2 beta hydrogens over here. And what's the difference between the beta hydrogens 1 and the beta hydrogens 2?
Beta hydrogen ones are primary.
Correct. And beta hydrogens 2 are secondary. So if you were to form your double bond between the beta hydrogen 1s, you're going to form a di-substituted alkene. If you do it over here, you're going to form a di-substituted alkene. And if you form it over here, you're going to form a tri-substituted alkene. See where that goes? This is going to give you a double bond here and only 2 things attached to it. This right here is going to give you a double bond here with only 2 things attached to it. This right here is going to give you a double bond with 1, 2, 3 things attached to it. So which way do you think it's going to go? We're going to probably end up with this regioselective system. Now, what if we cleaved our beta hydrogen 1 right here? It could be either this one or that one, it doesn't matter. So we have our base come in, starts to form a bond with that hydrogen. The electrons from this bond here go in to form the double bond. The electrons here leave with the bromine. Concerted reaction happens all at once, E2, bimolecular. Okay, and that gives us our minor product. Okay, but wait, hold it. There's 6 of these and there's 2 of these. That's kinetics, right? There's 2 of these, but they make more stable. That's thermodynamic, right? And we're using heat to encourage the thermodynamic problem. So now we can use that same base and only use one of these 2 here. We're going to tug on this hydrogen. We're going to do the exact same thing, forming a bond here, breaking a bond here. These electrons are going to come down into the double bond, and then these electrons are going to leave. So these electrons are going here. These electrons are going, these electrons are going that direction. That is not correct. Sorry. These electrons are going to form a new bond here. These electrons are going to form that bond there. These electrons are going to go onto the bromine. And that's going to give us our major product. Okay. Okay. So when using a small base and heat, we have the preferred product is the more substituted product. Does that make sense? All right. And the whole reason comes down to the stability or the activation energy of the 2 different transition states. Okay. The transition state with the alpha hydrogens on the beta 1 hydrogens is higher in energy than the one on the beta 2 hydrogens. And therefore, this reaction's faster. Notice they're not that much different, which is why we get both products. But this reaction's faster, so we get more of it. And it's faster because it has a lower activation energy. Okay. And again, it's more stable because during this formation of the transition state, it's looking for the more substituted double bond. So when you're using a small base, you always get, well, your major product is always the more substituted. Okay, right there. Small base equals more substituted as your major product. Notice that because the difference isn't big enough here, we can't say it's the only product, but it's the major product because it's faster. All right. All right. So now let's think about the rate of the reaction. Okay. So in the case of SN2, the less hindered you are, the faster the reaction goes. Okay. In the case of E2 reaction, the more hindered you are, the faster it goes. Because that activation energy is lower to form the more substitute. And that means faster reaction. The activation energy is lower to form the more substituted, so the reaction is faster. Okay, so let's think about product stabilities and where we're going to go with this. Okay, increasing the number of R groups on the carbon leaving groups, therefore gives you a more highly substituted system and therefore more stable in your E2 reactions. Okay, so that being said, let's look at our primary alkyl halide here. And we're going to use a alkoxide. So this is a base right here. And we're going to have the only choice we have. We don't have, these are alpha hydrogens. These are on the alpha carbon. These are the only two beta hydrogens we have. We only have one choice. There's only one product possible. It makes the monosubstituted alkene right here. Now, do we have a competing reaction here? If this is a small base, we can get substitution because it's a primary. Okay, but let's look at our tertiary here. Okay, we can use a small base or a big base, and we have choices. We have these alpha hydrogens, and these alpha hydrogens. Okay, those are all the same. So it's only going to form one product. But it's going to make the disubstituted alkene, which is more stable, so it's going to make it faster. It's going to make it faster. Okay, does that make sense? More stable, faster. All right, so when we look at any E2 product, we want to predict the major isomer. In the substitution reactions, we're just saying we're assuming it just goes to completion, and we usually only get one product, right? Here, we're starting to have to pick out our major and minor products. So our major product is going to be the more substituted one using our base. The more substituted is usually more stable. And we have a name for this. This is Zaitse's rule, okay? And it has nothing to do with the enzyme. It's just a different guy, okay? So Zaitse's rule says the predominant product will be the more substituted product, okay? Now, we have another rule. So write down Zaitse's rule says the more stable product is usually the more substituted product. But usually is the important part. Okay, so if we think about this, these let's see, let's blow this up. And let's see. These beta hydrogens and these beta hydrogens are equivalent, right? Because we have a ring, they're on both sides, they go around. And these beta hydrogens are different. Okay. So beta hydrogens 1 are going to give a tri-substituted product. Okay, so that's going to give a tri-substituted product. Beta hydrogens 2 are only going to give a di-substituted product. So which one is going to be more favored? Okay, think about it. If let me draw the other product here. Okay, so that's a CH2. So it's only a di-substituted product. So it's going to be the minor product. Okay, so choosing your beta hydrogens is how you pick your major and minor product. You choose the beta hydrogens that give you the more substituted product. Okay. Now, yeah, okay. If we look at the relative reactivities, our tertiaries are always going to be faster than our secondaries, and our secondaries are always going to be faster than our primaries. Again, it's all this stability, that activation energy. Okay. Now, there is a caveat to Zaitse's rule, and there's something that breaks Zaitse's rule. We're going to talk about that. The caveat is that if you already have a double bond in your system, your double bond you're going to form a double bond that is going to be conjugated. Okay. Remember what conjugation is. Okay. Conjugation is when you have a double bond, single bond, double bond, single bond, double bond, like that. And it's conjugated because if you look at the p orbitals, all these p orbitals in those pi bonds can line up. That gives us conjugation, and that's more stable. Okay. So if conjugation is more stable, then the caveat to Zaitse's rule is if we already have a double bond, you want to put that double bond one single bond away from the other double bond. That makes it conjugated. Okay. So let's look at this right here. We have a double bond here. We have a, let's see, it's a secondary alkyl halide. We have these beta hydrogens, and we have this one beta hydrogen on the tertiary carbon. So we have a tertiary beta hydrogen here. We have a secondary beta hydrogen here. The tertiary beta hydrogen would give us a tri-substituted alkene. Zaitse's rule. But the secondary beta hydrogen is going to give us a conjugated double bond with another double bond. Okay, that's even more stable than the more substituted. Therefore, our conjugation is more stable than a tri or tetrasubstituted alkene. That's why it works. So it's not breaking Zaitse's rule. It's a caveat to Zaitse's rule. You're trying to form the more stable double bond. So we're not breaking the rule. We're just making sure you understand that the conjugated double bond is more stable. So let's look at the products here we get. In the first one, we get a single bond, double bond, single bond, double bond. So this right here is our conjugated fragment. Now our double bond here is only 1,2 disubstituted. It's only disubstituted. Okay. Now if we take it from the tertiary beta hydrogen, we would end up with a double bond, single bond, double bond, but this double bond is tri-substituted. Okay, so we would try to go that way, but wait. Conjugation is more stable. Therefore, the more conjugated product is the more stable product, and therefore it's the major product. Okay, this works with benzene rings too, because we have conjugation in benzene rings. So if we have an alkene or a benzene, we're going to try to put the alkene or benzene one single bond away from the double bond or the benzene, and then it'll be in conjugation. Okay, so let's look at these major products. We have the major product being the one that has a double bond, single bond, and then double bonds. The minor product is single bond, double bond. It's tri-substituted benzene. Okay, so bottom line is don't use Zaitse's rule to predict it when you have double bonds or benzene rings. You want to use the Zaitse's caveat that you want to be more stable and conjugations more stable. Questions on that? Okay. So that means that elimination, E2 elimination is regioselective. Okay. You're going to make the more stable double bond or series of double bonds whenever possible. Okay. So let's look at the effect of changing our base. Okay, a small base can go in and take a beta proton off of anything, right? A big base might not be able to get to one of the beta hydrogens. So let's look at this. We have ethoxide here, so that's a small nucleophilic base. But we have a tertiary alkyl halide, so we're not worried about substitution products. Okay, so we're going to take that and we're going to heat it up to 70 degrees to favor an elimination reaction. So we have a solvent here, and we have our strong base, and we're heating it. Okay, we're favoring E2 reaction. Okay, it's not because we have a strong base, not a weak base. We're not favoring an E1. So when we see this, we can get our more substituted product here and our least substituted product here. Okay. And our more substituted product is our major product, as we were predicting using Zaitse's rule. Okay. And because we have these beta hydrogens here, and this beta hydrogen is the one we eliminate to make the major product, right? So if we were to highlight that in red here, red. This is the hydrogen we're removing to make the major product. And these are the hydrogens we're removing to make the minor product. So these are way out there in the ends. This is kind of has this methyl group, and this methyl group next to it. So if you made a 3D map, you'd say, okay, that's a little more hindered, but we have a strong base and it's small. So we follow the rule. Okay, so now let's take a big base, T-butoxide, our classical big base. And the product ratio changes. Why? We're gonna use, these are gonna be making this, and this one over here, this hydrogen here is gonna be making that. What's the difference between these two methyl groups and the red beta hydrogen? They're way at the ends. They're like out there. They're primary, right? This is a secondary. This is secondary, and these are primary. We have a big base. The big base can't reach in to give all the beta hydrogens here to give our more stable product. And therefore we get the less substituted product. Okay, so this isn't breaking Zaitse's rule. This is called the Hoffman rule. Okay, so small bases, high heat give us Zaitse's rule. Conjugation gives us Zaitse's caveat. And big bulky bases give us Hoffman's rule. You're going to attack your primary beta hydrogens first, because they're easier to get to, therefore it's faster, therefore it's your major product. Okay. So that makes sense too, right? Because if it's too big, it has to hit those primaries first. It's faster. It's our major product. Okay, so let's talk about stereoselectivity. Okay, so that was regioselectivity, where we're going to put it, right? And we said that some things are stereoselective, meaning it's going to favor one stereoisomer over another stereoisomer, right? That's what stereoselective means. Okay, so the thing is that an E2 reaction is stereoselective because the more stable stereoisomer is preferred. So what's more preferred, the cis product or the trans product? Trans product, because of steric interaction. So when we think about this, we have a choice of these two beta hydrogens. One beta hydrogen is going to give us one stereoisomer. One beta hydrogen is going to give us the other stereoisomer. And I'll show that one next time. Okay, so what we're going to see is with our strong base, we're going to end up with this is our major product, our trans product is our major product, and that will give us our system. Now, look at the little thing in the box here. The carbon which the hydrogen removed is bonded to the two hydrogen will give us mostly E and some Z. If the carbon removed is from only one hydrogen, like it only has one hydrogen here, it will give us mostly anti-elimination or mostly Z. Okay. Gosh, I don't see why. Why would that work that way? Well, the reason we want to do this is, let's look back at our Newman projection. Okay. When we have a Newman projection and we have our things fully anti, right? That's our most stable. Our two largest groups, anti, is our most stable configuration. Okay. Well, it turns out to make the reaction happen, think about our transition state. We're pulling off the proton, we're putting those electrons in, we're kicking electrons out. That means the proton that's being pulled off has to be anti to our leaving group. Proton has to be so that these electrons can kick in, those electrons can kick out all at the same time. So it is favored for us to have not our hydrogen that we're removing and the leaving group here eclipsed, but to have them perfectly anti, or what we call anti-periplanar. Anti-periplanar. Okay. There's two reasons, right? This. Number one, this gives us the easiest way to have a base come in and something leave. These electrons can kick in, those electrons can kick out. It's easier to happen all at the same time. So when you have a choice, when you're not sure whether you're going to get the cis product or the trans product, you need to redraw it with your Newman projection such that your hydrogen that's leaving is anti-periplanar to your leaving group. Let's try that. Okay. So if we have our base coming in like this, and then those electrons kicking in and this electron's kicking out, that's actually in a staggered configuration. It has to wait till it's in this highest energy configuration. And then it's got to try to move all these electrons on the same side. In the other case here, we have our hydrogen in our anti position here. We have it in our more stable configuration, our staggered configuration. And now our base can come in and our elimination can leave. So how do we select which one's which? Okay, we might have to redraw our product just to make sure. Okay, so let's look at this is our product. This is our starting material here, and I'm going to redraw this as a Newman projection. And I'm going to draw it from, let's see, we want the hydrogen on the front. So I'm going to draw it from this perspective here. Okay. And so we're going to redraw that from that perspective, and we're going to do it with this right here. So I'm going to draw it from this perspective here. So I need to put my front carbon here. My hydrogen's up. So I'm going to put my hydrogen up. Methyl group's back. So it's going to be on this side of me. And the phenyl group, which is the benzene ring, I'm going to put over here. Okay. So is that the correct drawing for the front carbon on this Newman projection? Hydrogen up, methyl group to this side, and looking down here, methyl group's going to be that way. The benzene ring is going to be this way. All right. Now let's draw our back one. Okay. And then we have our bromine down. So we're going to have our bromine down, Br. And we have our hydrogen. Let's see, we're looking at it down this way. Hydrogen's out this way. So that's going to be over here. And our methyl group's going to be over here. Okay. Does that make sense? Methyl group is going to be back, so it's going to be that way. Hydrogen's going to be that way, and bromine is going to be facing down. Okay, so now our hydrogen here is anti-periplanar with our leaving group bromine. So that means this is the preferred configuration for the E2 to happen, which means when we take away this right here and this right here, because they're going away, look, our two methyl groups are on the same side. So our product's going to have the two methyl groups on the same side. And our benzene and our hydrogen are going to be on the same side. Benzene and hydrogen are on the same side. Does that make sense? Do you see why you have to draw it in a Newman configuration? Okay. If you draw it in the Newman configuration, you get the right isomer. Okay. So let's see if we switch just these two groups right here. Okay, so we have a different isomer, and let's draw our Newman projection again. And we're going to draw the Newman projection in a different color just because we want to. So let's see, we're going to draw our first carbon here. And again, we're going to look down this perspective of the same perspective here. And looking down that way, the benzene is behind. So the benzene is going to be on this side, right here. The methyl group is out, so the methyl group is going to be here. CH3, oops. CH3. And then our hydrogen is going to be up. Okay. All right, so that's right. So let's do the back one. And looking down there, our methyl group is back. So it's going to be this way. CH3. Our hydrogen's out, so it's going to be this way. Hydrogen. And our bromine is going to be anti-periplanar to our hydrogen. Okay, so now let's make our double bond by erasing this and this. And that makes that our, let's do it in this color. The methyl group and the phenyl group are going to be on one side. And the hydrogen and the methyl group are going to be on one side. So the methyl group and phenyl group on one side. Oops. The hydrogen and the methyl group are on one side. And I got to turn my keyboard off when I lecture because I put my hand down too much. All right, let's do that on that side. Okay, does that make sense? All right, so make sure you draw your Newman projections. Okay, so that makes this a stereoselective reaction. When you line up your antiperiplanares, you're going to have one isomer as your preferred isomer. Okay, so this is another way to look at it here. You want to always draw your Newman projection and you always want your beta hydrogen you're removing to be antiperiplanar to your leaving group. So notice we have two choices for hydrogen here. Okay, you have this hydrogen and this hydrogen if you rotated this around. But what's wrong with that? Right now, your two largest groups are anti to each other. Okay, in the second one here, your two largest groups are gouged to each other. Here they're anti, here they're gouged. Which of those two Newman structures is more stable? The anti. So it's going to spend more time in the anti, and you still have a hydrogen antiperiplanar to your leaving group. So your major isomer is going to be this one. Even though there are two hydrogens to choose from, this is more stable than this one, and therefore your major isomer is going to be here, and it's the more major product because it's more stable. It's more stable in that antiperiplanar position. This is going to be your minor product because it's less stable in that antiperiplanar position. Okay, so it's not a mystery as to what your major product is. You just have to follow Hoffman's rule, Hoffman's caveat. I'm sorry, Zaitse's rule, Zaitse's caveat. Well, Hoffman's rule, and always draw a Newman projection if you think you're going to have them in different places. All right. So let's do a few other examples here. And if we look at this one right here, we have a choice of our primary beta hydrogens here and our secondary beta hydrogens here. So what's our major product going to be? We're going to remove secondary beta hydrogens first, right? Because those are going to be faster, and that's going to give us our major product. So our major product is going to give us our 2-butene, okay? Now, because there's probably going to be one of those is going to be a major product between the cis and the trans, one's going to be major product depending on the Newman projection. So you could go actually redraw that and figure out the Newman projection and see which one's more stable and see whether the cis or trans isomer is going to be within that set, going to be more pronounced or have a greater amount. And of course, our less substituted is the minor product. And we don't have a stereochemistry problem. Now, let's look at this one right here. We have a tertiary alkyl halide. We have no beta hydrogens here, so we don't have to worry about that. We have a beta hydrogen here and a beta hydrogen here. This beta hydrogen, let's redraw that with the blue here. Blue. Maybe I should just get it to change colors there. The blue beta hydrogens here is going to give the less substituted product, right? The red beta hydrogens are going to give the more substituted product, okay? So we're probably going to get a major product where we're going to form the double bond here, right? But we need to pick whether it's going to be, is this the E or the Z product? So you cut it in half. This is the highest priority group here. Cut it in half. This is the highest priority group here. So they are on opposite sides. So that makes this the E product, right? So this is the E product. E. And then we look at the minor product here, and the minor product is Z product right here. Okay. Why? The Z products, the more that the two largest groups opposite each other is more stable. If the two largest groups are together, it'll be less stable. That means that in the Newman projection, these two groups were gauche. In the Newman projection, these two groups were anti. Go draw the Newman projection and prove it to yourself. This is gauche. This is anti. And if you draw that Newman projection, you will be amazed. Okay. All right. Next. Cyclohexanes. Okay, cyclohexanes, we like to use a lot to measure stuff like, stereochemistry, because it's locked in a ring. We can see what was the top and what was the bottom. Okay, so we like to use it there. I know they're hard to draw, but it shows us a lot of information. That's why we use it. Okay, so let's look at this one here. We have two different, no, we have two beta carbons, and they have the same beta hydrogens, right? So we have two kinds of beta hydrogens now, right? We have axial beta hydrogens, and we have axial beta hydrogens. Sorry, I said that wrong. Axial beta hydrogens, and we have equatorial beta hydrogens. Okay. And our chlorine here is in the equatorial position. Are there any hydrogens anti-periplanar to that chlorine now? No, because the thing that's anti-periplanar to that chlorine is the methyl group here, the CH2 group. Okay. So can this configuration eliminate? No, there's no hydrogen anti-periplanar, and there's no hydrogen that's eclipsed. So both of these hydrogens cannot be removed to give us our major product. But let's go ahead and go to chair 2. Let's go to chair 2 now. Just flip it over, go to chair 2. Now we have our chlorine in the axial position and our two different beta hydrogens in an axial position. That product will eliminate. And we're going to eliminate, giving us the double bond on one side or the other. So when we don't have a hydrogen anti-periplanar, we get no reaction. No elimination products. But if we can put it into an anti-periplanar position, we get our major product, which is our alkene. Questions on that? Okay. All right. All right, so let's take that to another level. All right, so now we have two big groups on our cyclohexane. Okay, the two big groups on our cyclohexane we want to have in the equatorial positions because that's more stable, right? When we have that, we have our chlorine is in the axial position. We have a hydrogen in an axial position. Okay, which means we can get our elimination product here. So our elimination product is going to be here, okay? Because that configuration is more stable. Now, if we go to this position here, there's no hydrogen that is anti-periplanar to that chlorine. So it's not going to react. It has to wait until it goes back to here before it reacts. Okay, so let's change it a little bit. We're going to change the isomer. We're going to have, instead of the chlorine being in the axial position in the more stable form, we're going to move the chlorine to the equatorial position in the more stable form. Okay, now that means that there's no hydrogen anti-periplanar to this chlorine right now, right? Because it has to be in the axial position to have one. So it has to wait until it goes to this configuration. And in this configuration, the hydrogen over here is not anti-periplanar. Only the hydrogen over here is anti-periplanar. So this hydrogen is not anti-periplanar, so it's not going to form the more substituted product. We form the more substituted product here, right? Because we have the 1, 2, 3 substitutes is here because of this. Now we've moved that chlorine, so we have to change the configuration to get us to anti-periplanar. That means the double bond is going to form here, so it's only di-substituted. Okay, so even though we're following all the rules, you must have it anti-periplanar to get your major product. And therefore, when we're flipping our rings, we're flipping our position. So this is in a different position than this stereochemically. And because of that, it forms a different product. When in doubt, draw the Newman projection. Okay, questions on that? Okay, so now let's take this one step further. Okay, we want to form the Zaitsev product, the more substitute product, but we also know we have to have our leaving groups and our thing anti-periplanar. So we have to keep flipping our we have to keep flipping chair to one, chair two, until we have that available position. Now, in this case right here, we actually have only one hydrogen in the axial position and one in the equatorial position. So we can't form the more stable product. We can't form, this would be the more substituted product. So again, we form the less substituted product because it's anti-periplanar. Okay? All right. You're gonna have nightmares about anti-periplanar. All right, so let's go to that caveat of Zaitsev's rule. And that is you're going to form the more conjugated product when possible. Okay. But what if you don't have an alkene on your system at the beginning of the reaction? What if you only have two halogens? Okay. Well, what's going to happen is you're going to remove one of those halogens, and that first halogen to be removed will follow Zaitsev's rule. The first halogen, if you have no double bonds, is going to follow Zaitsev's rule. So that means we're going to have the more substituted alkene form. Okay. So this is following Zaitsev's rule. But now you have a double bond. And when you have the double bond, you have to follow Zaitsev's caveat to give us the less substituted one, but in conjugation. Okay. So just remember, if you're doing a two-step elimination, look for where the double bond was. You're going to form your major product is the one that's going to be more substituted. And then you look for conjugation. Questions on that? All right. Okay, so, and this is the whole reason, because you're going to attack one or the other. Whichever one you attack, you're going to end up making the more substituted alkene. Okay, now you have to make them in conjugation, which is forcing you to not to use this tertiary, not to use the tertiary halogen, but using the secondary halogen, the tertiary hydrogen, the beta hydrogen. We're going to use that secondary beta hydrogen because it's in conjugation with the first. So the conjugated one is going to give the more stable product. The unconjugated one is the less stable product. Yes.
What if your second halogen is too far away where it can't be conjugated?
If it's too far away where it cannot be conjugated, it follows Hoffman's rule. I'm sorry, Zaitsev's rule. If it's like, see, this is a 1,2,3 1,3 dihalogen. If it's a 1,4, Zaitsev's rule all the way. Both of them. Only in 1,3 dihalogens can you do this. Or if you already have an alkene and your halogen is one methylene away. So a CH2 and then where your halogen is. Then it'll be conjugated. Okay. All right. Okay, let's see. All right, yeah, let's just get to the summary and then we'll take a break. Okay, so if we have two halogens on the same carbon, we call that geminal. Geminal, meaning twin. Okay, so two on the same carbon, that's a geminal halogen right here. So we call that a geminal dihalide or geminal dibromide in this case. Okay, so if we just use a base like hydroxide or something like that, you can only remove one of the beta hydrogens. Hydroxide's not strong enough to remove the second beta hydrogen. Why? When you remove the first beta hydrogen, you now have a double bond and the basicity or the acidity of that proton changes. So you need a stronger base to remove that second hydrogen. You have changed the hybridization of that carbon. So now we have to use a stronger base than the hydroxide, which in this case is called sodium amide or potassium amide. You can tell it has a negative charge and two hydrogens on a nitrogen. And when we do that, that's strong enough to remove that second hydrogen and halogen. And when you do that, you go from your double bond to your triple bond. So this is how to make alkynes. We're doing a consecutive E2 elimination using a geminal halide. But what if they're on the 1 and the 2 position? We can do the same thing. We're just going to remove one of the halogens on the, let's call that the 1 carbon. And we'll form a double bond, and then we'll have to remove the second halogen from the 2 carbon. But again, we have to use that base, that stronger base. Now, if they're on the 1, 2, they're called vicinal or neighbors, for lack of a better word. They're approximately together. This is geminal for twins. This is vicinal for nearby. Okay, but you can only use sodium amide. So this is important because when we're trying to make alkynes, 2 requirements are required. You must have 2 halogens and 2 hydrogens that are removable on the 2 carbons you're looking at. And they need to be vicinal or geminal, and you have to use sodium. You have to use amide, sodium amide, potassium amide. Okay. All right. So our summary for this is that our E2 mechanism is second order because both things have to be at the same time. It is a one-step mechanism. Tertiaries are faster than secondaries, are faster than primaries, and it's favored by strong bases. Okay. You favor the more substituted group. The leaving group, the better the leaving group, the better the faster the reaction. Iodine's faster than bromines, faster than chlorine. And we favor polar aprotic solvents because polar protic solvents promote carbocations. We don't want to promote a carbocation because that'll be an E1 reaction. So polar aprotic solvent. Okay. The E2 reaction is regioselective in what double bond we form, and stereoselective because of anti-periplanarism. SN2 reactions often compete with E2 reactions if you have small bases. So the bigger the base, the more likely you are to have an E2 reaction, and especially if you have a primary substrate. Primary substrates, you get a lot of the substitution product, but you can favor the elimination product by heating it. You can favor the product by heating it. Now, the E2 reactions do not undergo rearrangements because there's no carbocation. So they're very clean reactions. Do them hot, big base, aprotic solvent, and you have no side reactions. You'll only end up with 2 products, your more stable alkene and your less stable alkene. Reactions with alkyl halides are much more useful than in E1 reactions because rearrangements, side products, competing SN1 reactions. All right, I'm going to take a break and then we're going to go with an E1 from that. All right, 5 minutes, smoke them if you got them. I'm kidding, don't smoke. Okay, I'm not going to pause because I will forget to turn it back on. Yeah, I'm trying to get caught up on all my grading by our next exam. In fact, I plan to have the next exam graded by the evening and posted because the data drop with a W is Saturday. I don't think anybody needs to drop with a W. I think we're all doing well enough that we don't have to do that. If you think you need to talk to me, please come and talk to me before you drop. Because, you know, with the redoing the exams and all these things, we should be able to come up with a way to, you know, make sure that you have extra time to work, or we come to my office hours, we'll make sure it happens. Well, we'll make sure you get it. Well, we'll try very hard. Okay. Oh, Yeah. Introduce yourself.
Oh, hi guys, I'm Amy. I work at pharmacy and HEB, and I have a bunch of like COVID tests, so I brought them here. If you guys want them, just leave them at the front, take whatever you need. Yeah, no problem.
So do you know Clay?
I do play actually.
Clay was one of my research students. So
HEB,
Oh.
But
Oh.
I do work biology.
okay, because he worked at the one here and okay. I like Clay. Yeah. I need to ping him actually. He needs to come and get his lab coat for my office. So, all right, give it 3 more minutes here. Get up, stretch. Do cat yoga. The only problem with these true N95 masks is that these just they get pulled out real quick. You know, because I could wear my KN95s for several days, and these are good. You know, good for like barely a day. So, yeah, but I mean, you can wear it all day because it does seal really well too. It doesn't even fog up my safety glasses. So. Okay, couple more minutes here. It's not easy to stand up here and talk for an hour and a half. So. But I've kept almost everybody awake.
I don't think any of us would be that mad if you were sitting down.
Oh, no, I don't need to sit down. I just, you know. Well, I actually, when I broke my foot last semester. I had to sit down for a part of the lecture. So, just the outside bone on there. I hit it on wheelbarrow gardening right before spring break. Right before my wife and I went down to South Padre for our 31st wedding anniversary. So they were very slow walks on the beach. But we had fun, and actually she had more fun than normal because I didn't say, let's go up and let's go do something. Let's do this. I'm like, I'll just sit here. I'm good. I'll just read my book. It's probably the best anniversary of her.
Was your wedding chemistry team?
No, it was not, but it was on spring break, and we were both taking CHEM at the time. So we were it was scary. So we got married here down at the river, down at the park there where the was it Sound of Christmas. There's this little house called the Fish Factory building. We got married in that building. So all right, enough about me. All right, let's go. Yeah, 11 o'clock. Let's reconvene. All right, got it. All right. Okay, so now let's talk about E1 reactions. Okay, those were all E2 reactions. We had nice stereoselectivity, we had regioselectivity. We had to form, we knew what products we were going to form. Okay, because we had our nice rules. Zaitsev's rules, Zaitsev's caveat, and Hoffman's rule. Okay, so now let's see how things change when we go to our E1 mechanism. Okay, first of all, our E1 reaction is regioselective because you have to form your carbocation where your leaving group was, and then you form your next product from it, right? So when we look at our tertiary alkyl halide here, we can see that it is going to, of course, remove this proton, and it will favor the Zaitsev's product. Okay, we're going to form our carbocation here. We're going to form our major product is our Zaitsev's product. So it is regioselective. selective. Okay, now the alkyl halides, the better the leaving group, the easier it is to form your carbocation. So the iodines are going to be faster than the fluorines here. Okay. What's the other thing we have to be happening here to make our E1 happen? We actually have to have two things. We have to have a poor base, and we have to have a protic solvent. So a lot of times when we're looking at an E2 reaction, water is the base, or alcohol is the base. Remember, those are Lewis bases because of lone pairs, but they're not strong bases because they don't have a negative charge. Okay, so that being said, we still have regioselectivity. All right, so just like before, formation of carbocation is the first thing, which means tertiary alkyl halides are faster than secondary alkyl halides, and our methyls and primaries don't happen at all. Okay, which means if you have a primary alkyl halide, you're probably going to have to do an E2 reaction. And you can't do an elimination reaction with a methyl group. There's no beta hydrogen. Okay, so that makes pretty much good sense, right? Now we have to think about what's going to happen, where our double bond's going to end up, because carbocations rearrange. Okay, so let's look at here. Okay, oh, we already have a double bond. So we're probably going to follow that, trying to get them in conjugation. Now, before we had to have it in the 1,3 position, right? Because it had to have that one space between them. But now that we form a carbocation, we can rearrange. So it makes it easier to form the conjugated product. So let's look at this here. We actually have it in our secondary here. Oh, this is a secondary alkyl halide here. But what's going to happen when we form that carbocation? Look here. We're going to form that carbocation here, right here. Now we have a problem. That's a secondary carbocation. Can it move to make a tertiary carbocation? No, but it can move to make an allylic carbocation. Benzylic and allylic carbocations are more stable than tertiary carbocations. So it's going to rearrange. It's going to rearrange to put the double bond next to, I'm sorry, the carbocation next to the alkene. Now, when it does that, it can just now eliminate the hydrogen it just moved and give us the conjugated product. But notice the mechanism is slightly different. It's not just removing the beta hydrogen that's next to the alkene. It actually moved the carbocation next to the alkene because the allylic carbocation is more stable. It still gives us the same product, but it did it in a different mechanism. So that same thing happens with benzylics right here. Notice that there are no beta hydrogens here. So, well, it can't be conjugated, right? No, what happens in carbocations? 1,2 hydride shift, 1,2 methyl shift, ring expansion to rearrange to make a more stable carbocation. So what's going to happen here is it's going to form its secondary carbocation. And it's help me, I don't like being here. I'm going to do a 1,2 methyl shift, giving us our carbocation here. Now we have a beta hydrogen that's in conjugation with our benzene ring. We're going to eliminate that beta hydrogen and we have our alkene there. And we've moved a methyl group. Okay. So E1 reactions rearrange. Always look for rearrangement when you have a carbocation. 1,2 hydride shift, 1,2 methyl shift, ring expansion. Okay. So, and again, the whole idea is that you want to form the more stable carbocation. Secondary is okay, tertiary is better because of hyperconjugation and induction. Allylic and benzylic are conjugated, hyperconjugated, and inductive. They add all of them together. So they're more stable. Okay, so in the case of this one right here, we're also going to look for where that carbocation is going to be. Now, the cool thing about a carbocation is, remember, it's already changed hybridization. It's already gone to sp2, and it has a p orbital that's empty. Okay, so it's trying to line up the electrons that are being pulled away from when the hydrogen gets pulled away, those electrons are going to fold back down. That's going to give you selectivity. And in fact, it's going to give you the E isomer most of the time. Because the E isomer is going to give you the more stable one that has the big group away. Okay, so we're going to get the E isomer most of the time. So let's look at forming our carbocation here. We have a tertiary carbocation. Is that going to rearrange? There's another tertiary. No, you're already tertiary. It's not going to rearrange. Only secondaries rearrange. Or tertiaries unless you're going to allylic or benzylic, but it usually doesn't happen. Anyway, so now we have our carbocation is going to form here. And our this is now trigonal planar. That means your biggest groups are going to be trying to be away from each other. So that means this group right here is going to just try as far away from that one as possible. That way, you end up with the Z isomer as your major isomer. That makes sense? You've already changed hybridization on your carbocation, and therefore, it's going to try to turn around to get the biggest groups away from each other and give you that hydrogen. Now, do you have to be anti-periplanar? Well, that doesn't exist here because we don't have the leaving group in the hydrogen. It doesn't matter. All you have to do is line up your p orbital with the hydrogen that's being pulled off. And that means it can pull it off from the top or the bottom. But the sterics is what's giving you the E isomer as the major isomer. Does that make sense? Biggest groups farthest apart. Okay. Now in rings, you might not be able to do that all the time, but let's talk about it. All right. So let's see what we have happen in rings. Okay. Again, we don't have to have a hydrogen in the axial position because we've already changed the hybridization. Okay. So in the case of here, we can have our chlorine in the equatorial position. Doesn't matter, it's leaving first. We get a trigonal planar intermediate here, which means any hydrogen, the top hydrogen or the bottom hydrogen, the hydrogen that's axial or the hydrogen's equatorial, it doesn't matter, it can leave and give us our bond here. Notice it has it can take the axial hydrogen on the more substituted carbon, or there's an axial hydrogen right here too, but it favors the more substituted product. It's got two choices that still favors the more substituted product. Okay. Now, if you can rearrange, you will. Now, this is a 6-membered ring, so we're not going to do a ring expansion, but it can move to give you something more stable. So in this case here, we have a secondary alkyl halide, which is going to give us a secondary carbocation. It's not going to move that way because that's going to give us a secondary carbocation that way too. Secondary, that's what it is. But it can move this hydrogen over 1, 2 and give us a tertiary. And if it gives us the tertiary here, it'll actually give us the tetrasubstitute product again. Even though this leaving group was not on one of these 2 tertiary carbons. Remember, the leaving group was on the tertiary carbon here and gave us our more substitute product, tetrasubstitute. We're going to do a 1,2 hydride shift to give us our more stable carbocation before giving us our more stable carbon. Okay. And yeah, so actually, let's go to 1,2 shift, giving us that. All right, questions on that? So E1 reactions have that problem. So it's a first order reaction because you have to break it on first. You form a carbocation, and therefore you are going to rearrange if you can. Okay. The mechanism is 2 steps. Tertiaries are faster than secondaries or faster than primaries. And primaries almost never happen. Favored by weak bases such as alcohol and water. What also are alcohol and water? Protic solvent. Okay. The better leaving group makes it go faster. So iodine's faster than bromine, which is faster than chlorine. And of course, protic solvents because they solvate both anions and cations. The E1 is regioselective and stereoselective, just like before. Stereoselective is the E and Z, right? We form the E because we want the 2 biggest sides away from each other because we've already changed the hybridization. SN1 reactions often compete with E1 reactions because you can have the base, instead of having the water act as a base, you can have the water act as a medium. E1 reactions often go rearrangements and are much less useful than your E2 reactions. In fact, you can't even do a primary alkyl halide in an E1 reaction. You have to do it in E2. All right, questions on E1 mechanism? Okay. So let's compare and contrast just like we did with the E1, the SN1 and SN2. Okay. E2 is stereoselective. The hydrogen is removed to give mostly E and some Z. Okay. Unless you're required by the anti-pluriplanar to give a different product. But even then, you wanted the two biggest groups anti to each other if at all possible. So E is still favored. Removed from the give it's the most anti-elimination, which gives us the most E. And E1 is mostly E as well, because you've already changed the hybridization of one of the carbons. In the stereochemistry, we want to see that SN1 always gives racemization. You have an orbital on top, top gives one isomer, bottom gives the other. SN2 always gives inversion. E1 gives mostly E. E2 gives mostly E unless you have an anti-periplanar configuration that yields Z. Okay, so you have to look for that on occasion. All right, so one more time, most useful. Selecting your base makes it easy. You don't have any competing reactions. You can do it with primary, secondary, or tertiary. It's most useful. Favored for strong negatively charged bases. And if you have a primary, you want to use a big bulky base because you want to eliminate any possibility of it doing a substitution reaction. Tertiary alkyl halides react faster than primary or secondary, but again, bulky bases ensure that you get the reactions to go. You always have a competition in E1 reactions, so it makes it much less favored. It's favored by weaker or neutral bases, and it's favored, and it doesn't react with primaries. In fact, when you looked at the chart we made yesterday, when you looked at weak bases and primary alkyl halides, it was no reaction. No reaction. Can't form that primary carbocation, therefore no reaction. You must do an E2. All right, so that's dehydrohalogenation. Okay, dehydrohalogenation is a base-mediated reaction. Meaning you have one equivalent of base at least for each equivalent of acid you remove. Okay, so it's a base-mediated reaction. Now we're going to go to something a little different. We're going to look at dehydration. In the case of dehydration, we're going to remove one equivalent of water instead of one equivalent of acid. Okay, now hydroxide is a horrible leaving group, so we're going to acid catalyze our system, meaning one drop of acid is enough to do our dehydration. Okay, and I'll explain one. So we can make this by adding acid and heat. Remember, heat promotes elimination reaction. We usually use an acid, something that's strong acid. This is we usually use the strong mineral acids or the classical sulfuric and phosphoric, but you can actually use Lewis acid. Anything with an electron deficient center can help the reaction. Okay, so acid isn't required, but it can be a protic acid or Lewis acid. Okay, and primaries take much more heat. It's harder to do primary alcohols, to dehydrate them to get our terminal alkenes. Secondaries are better. You don't have to heat them as much. And tertiaries are even better. They're lower heat. Now that's because the primary alcohol is required to go through an E2 reaction. Why? Primary alcohol can't form a carbocation, and therefore it can't go through an E1 reaction. It must go through E2. The other two will go through E2 reactions, okay? So that means tertiary alcohols are faster than secondary alcohols, which are faster than primary alcohols. But primary alcohols work, they just change mechanism. Okay. So let's talk about the E1 mechanism for the secondaries and tertiaries first, because that's easy. Okay. So we have an acid catalyzed system, which means we're going to use the proton. We're going to do one of those 5 things in the mechanism. We're going to add a proton to the alcohol here to give us a protonated alcohol. Because hydroxide is such a bad leaving group that if we protonate the alcohol, now we have water leaving as our group. Water is a good leaving group. It's a neutral molecule. That's why we do it. We're making OH a leaving group that is a good leaving water. So when we do this, we have our protonated alcohol, then we can kick out our electrons, giving us our neutral water. Now notice that when we have our acid here, this is our hydronium ion. And when we protonate it, we get water out of there. Okay. So now we just kicked out another equivalent of water. Okay. And we formed our carbocation. Okay. Now water is going to act as the base. Water is going to remove your beta hydrogen. And when water removes your beta hydrogen, you get your alkene, and you've regenerated your hydronium ion. That's why it's catalytic. You regenerated your hydronium ion. You kicked out one equivalent of this. You started with hydronium ion. You ended with a hydronium ion. And you kicked out your alkene. This is the E1 mechanism for secondary and tertiary alcohols. Okay, questions on that? So in primary alcohols, we have to do things a little different because we can't form that carbocation, but we still do the steps in the same way. The first step we do is we take our acid and we protonate our alcohol. Okay, so now we have our protonated alcohol and we have something that's a conjugate base. We just made a base. We started with an acid, we protonated our alcohol, now we have a base. What can the base do? Remove a beta hydrogen. So now we have our base in our system. So we have our acid come in and act as our conjugate base here, come in and act as a base, removing our beta hydrogen and giving us our alkene. But then look what it did. It generated our acid again. So again, it's catalytic. One drop. But notice the mechanism is different. We had to protonate, generating a conjugate base. The conjugate base removed the beta hydrogen, regenerated the acid. All right. Does that make sense? And again, it doesn't go through the E1 mechanism because that would make a primary carbocation. So it had to go through the E2 mechanism. You look concerned.
It's like trying to like, check it out.
Okay.
I was looking.
Okay. So the key step here is that you started with an acid, you transferred its proton, it became the conjugate base. The conjugate base is the base that removes your beta hydrogen, regenerating your acid. So your conjugate base is the base. We didn't start with a base. We made a base, and then we regenerated our acid. Okay. All right. So let's talk about the problem with, the E2 dehydration. One of the things about the E2 dehydration here is that we have side products. Because once you create your protonated alcohol, you have a primary leaving group now. You have a primary leaving group. So if you have a nucleophile, something that is more nucleophilic than basic, then you can get substitution reactions. Okay. So in this case here, let's say we're doing our reaction in ethanol here, and we're actually trying to make ethene. Okay, so we're trying to actually eliminate this to give us ethene. So we have a drop of acid in there, and we take our alcohol here, we protonated our alcohol. It can't form a carbocation, so it's going to C here, but now we have a leaving group. So now another equivalent of alcohol, look, we have lone pairs. our lone pairs can act as a nucleophile and displace our water. And when we do that, we generate this protonated ether. And then then we can have any old base come in here, maybe another equivalent of ethanol here, come in and remove this proton, and we have a substitution product as a byproduct. Okay, and it's because we were trying to do an elimination here, but we still had something in there that was nucleophilic. We didn't just have bases, we had a nucleophile now, and therefore we got substitution products. Okay. Questions on that? So this is actually a byproduct with our primaries. You don't get that byproduct with the secondaries or tertiaries. So that means the carbocation-based system is more synthetically useful to make alkenes. Here you're going to make some alkene, but you're also going to make some ethers. Here you only make your alkenes. Okay. So no side products, no good nucleophiles. Yeah. All right. Does that make sense? All right. So this is just what I said. Oh, and it again, we'll try to follow Zaitse's rule if at all possible. Everything else, yeah, I need to update this slide. All right. So can we prepare? Okay, so that was 2 ways to make alkenes. Okay, we have 2 ways to make alkenes. Okay, so when we do our reaction tables tomorrow, we're going to have to put those on our thing. We have 2 ways to do it. We can start with alkyl halides. We can start with alcohols. Okay, but we also saw that we could make alkynes starting with a dihalide, right? Okay, so when we look at this right here, to make alkynes, we can do it by elimination, but it has to be 2 steps. One equivalent of the alcohol, one equivalent of the acid comes off first, and then the second equivalent of the acid comes off, generating our thing. And again, this reagent right here, sodium amide, when you see alkynes, think sodium amide. When you see sodium amide, think alkyne, because we're going to use it for other things too. And it's usually used with alkynes. So sodium amide and alkynes run hand in hand. Okay. And we can also use, if they're vicinal, T-butoxide, but only if they're vicinal. It doesn't work if they're general, only if they're vicinal. And so we can generate an alkyne that way as well. Now we have one crazy weird reaction that we can actually also make them. And it's weird because you start with a ketone. And it's weird because when you start with the ketone, you're actually going to have the phosphorus compound add 2 chlorines. So you're going to get a geminal dichloride, but that phosphorus is also going to rip off that oxygen. When that phosphorus rips off our oxygen, it generates POCl3. Okay. Notice this is a 2-step method now. We can convert this ketone into a dihalide. And then when we add our sodium amide, notice where we form the triple bond. We can't form the triple bond here. We could form the double bond here, but it's actually favored to form the triple bond to give us our alkyne. Of course, some of it is the double bond and it stops. That's why the yield is so low. All right. Let's see, where are we? All right. So I said before, when you see sodium amide, think alkyne. You see alkyne, think sodium amide. Here's why. We have a opportunity because the proton on the alkyne is the most acidic carbon hydrogen. And it's the most acidic carbon hydrogen because of its hybridization. Okay. When we look at the pKa of our acetylene, that hydrogen has a pKa of 25. And that's because it's sp hybridized. Half S, half P. Remember, S is smaller, holds electrons tighter. Okay. Therefore, it's more willing to support that negative charge. It's more willing to support that negative charge, so it's more acidic. Now, if we go to sp2 hybridized, it's 1/3 S. So it drops from a half to a third. And the acidity goes down. The pKa goes up because it's holding those electrons less tightly. Therefore, it's less stable. Therefore, it's less acidic. And when we go up to our sp3 hybridized, that goes even higher. So we can take advantage of this. Okay. If those electrons are being held tightly by that half S character, half P character, we can deprotonate that alkyne and turn it into a nucleophile. Okay, so when we turn that into a nucleophile, we call that the acetylide ion. And to make the acetylide ion, we use sodium amide, a strong base, usually sodium amide. Okay, so when we do this here, we can make the acetylide ion right here, and then we can use it to attack any electrophile. But we have to use a strong base that is not OH and not OR. We have to use sodium amide, or what this little thing is, hydrogen negative. That's what we call hydride. And there's a reason for this. Okay. Sorry. All right. And the reason, we're actually going to talk about that in the next chapter, but okay. So the utility of this is great because this is a way to make a carbon-carbon bond. Okay. So if we looked at all of our SN2 reactions, most of the time we're attacking with negative ions, right? So the only two to make a carbon-carbon bond are the acetylide ion and the nitrile ion, the cyano ion. Those are the only two to make carbon-carbon bonds. So we can extend the chain by 2 carbons every time we do this, and then we can get rid of the alkyne if we want to. Okay. So think about this: is we now have a great nucleophile. We have a primary substrate here, so we're going to do a great SN2, and now we've made a 1-carbon substrate into a 3-carbon substrate. Okay, so this is great. This is a great way to do it. And in here, we've made a 2-carbon substrate into a 5-carbon substrate by having only 1 hydrogen to remove and a methyl group on the other end of our acetylene. Okay, but we can do this stepwise too. We can take this right here, react it with a primary alkyl halide on one side to give us 1 methyl group. We still have an acidic hydrogen. We can remove this one right here and react it with something else on the other side. So we can make it unsymmetrical. We can make it long. We can make it a ring. We can make it all sorts of stuff. So that's going to be important. Now, unfortunately, by the time you get to primary and secondary alkyl halides, it's too bulky, and it stops acting as a nucleophile, and it starts acting as a base. So you end up with elimination products. So secondaries and tertiaries give us E2 products. Primaries give us substitution products. Because think about it. Think about the acidity of that proton. It's a very, very weak acid, 25 pKa, which means when we turn it into its conjugate base, it's very, very strong base. But it's still a nucleophile, but it is still a base. So, all right. So, actually, let's stop here, and I will continue this tomorrow when we're talking about catalytic hydrogenation. Okay. And then we have an activity tomorrow, which is our reaction tables. And then we'll start, what is today, Wednesday? We'll also review for our exam. I'm gonna review the second half of chapter 5, chapter 6, and chapter 7. Okay. All right. I'm gonna go ahead and stop recording.